Good afternoon, everybody. Welcome to the seminar. I do not know to which extent I need to introduce to you Professor Colin Meyer. He has been with us here for about 5 years now, and he's one of our specialists on glaciers, among others. Well, I'm still going to introduce you a little bit. Yeah, Colin came to Dartmouth after getting his Bachelor's of Science in Civil and Environmental Engineering from the University of California in Berkeley. From there, he crossed the ocean, went to Cambridge University on a Winston Churchill scholarship, and got a master's degree in applied science at Cambridge University. Crossed the ocean back to the east coast of the United States and got his PhD at Harvard in applied mathematics. And along the way, he attended the McCartney Glaciology Summer School at the University of Alaska, which gave you the first taste of polar regions and glaciers. And then he was also a fellow, predoctoral fellow at the Geophysical Fluid Dynamics Institute at the Woods-Hole Oceanographic Institution. Quite some achievement there. And went on to do a postdoc at the University of Oregon, with Professor Rampel over there, working on frozen subglacial sediments. So it seems like that's when you started narrowing down your topic. And today is going to be talking about his active research topic, which, as you can tell from the title, has to do with how glaciers are sliding away and, creating possibly some problems in the context of climate change. The floor is yours.
Thank you. Yeah, thank you, Benoit. It's nice to be here. As Benoit said, I'm Colin, for those of you who haven't met me before, and I study glaciers. Here's a photo that I took out the window of a helicopter in Greenland. We have a field site in Greenland that we go to for the past 3 years now. And so I like this picture because it shows a bunch of different pieces about what glaciers are about and how they interact in the climate system. So we'll just start here. This is a glacier. It's called the Han Glacier. It's just for Greenland, this is just a sort of a nothing glacier. It's just a small glacier. If it was in the United States, it would be like the biggest glacier around. But you can see up here, this is the Greenland ice sheet. And this is where the snow falls throughout the year. It compacts under its own weight. And then as it compacts, it turns into this sort of plastic material that flows like a viscous fluid, like very viscous maple syrup. And it flows down into the ocean. Here are some rocks. Here are some hanging glaciers. And you can see that the glacier interacts with the ocean here, where it breaks off and forms icebergs. These chunks out here, these are just rafted pieces of sea ice. And you can see that there's a bunch of bergy bits in here as well. And if you look here in the front, and this is the reason that I took the photo, is that there's a little bit of a dark patch right in the front. And that's evidence of subglacial meltwater that's coming down from underneath the glacier. It's mixed up with a bunch of sediments, and it's buoyantly rising to the surface. So I like this picture because it illustrates a bunch of different pieces about our research program here. Okay, so as a way of introduction, I work on lots of different things. The threads that are tying together my research program are phase change, ice, sort of societal impacts, and then climate change. And so when I'm looking at glaciers and snow, I'm thinking about, what are the boundary conditions and how are they affecting the glacial motion? And so those are the pieces here. I'm interested in snow, both in the alpine context and on the surface of glaciers. That's sort of the zeroth order question in glaciology, is how does the snow that falls on the surface affect and the mass balance, the sort of like bank account of glaciology. I'm also very interested in what's happening at the base. So today I'm going to talk about subglacial hydrology. That is the water that's flowing along that interface, both from groundwater and from the surface meltwater that's getting in there, and also from friction. But as Benoit mentioned, I spent a bunch of time thinking about frozen subglacial sediments. And this also connects to work that I've done on permafrost. Permafrost is sort of like frozen subglacial sediments without the glacier on it. And this is very interesting because as glaciers are sliding along the interface, they're not sort of stuck to the sediments. It's both a mechanical interface, right, a sliding interface, one where there's, what we might think of as like a fault. But it's also a thermodynamic interface. So this is an image of a glacier in Antarctica called Taylor Glacier. And you can see these laminated and frozen sediments to the base of it, and then there's some just regular sediments below it. And so the glacier is sort of frozen to the sediments, where there is an interface in here where it's this part is frozen and that part is not frozen. And so it's coupled, it's thermomechanically coupled, right? You're coupling the thermodynamics and the mechanics of the system. And then lastly, something that I started working on when I came here to Dartmouth are these icy satellites. So, the amazing things you can do with clip art in Keynote. There's even a Jupiter form in clip art. I was pretty amazed by that. And so this is a little moon of Jupiter. How many people have seen Europa through a telescope? There we go. This half of the room has definitely okay. So this half of the room we should go out and look at it. So sometime hit me up. Let's do that. But it's a beautiful moon that you can see. And what are these icy satellites? They're sort of like little glaciers in the outer solar system. There's ice on the outside and an ocean on the inside. And the dynamics are driven by tides. Jupiter is huge. And so it has a huge tidal pull on these small icy satellites. And so the ice flexes about 14 meters every day. That's huge tides, and so they're sort of like ice shelves on Antarctica, which is this sort of floating extension of a glacier, but in the outer solar system, where the tidal processes are happening, the gravity is different, and they have a lot of astrobiological potential, right? Because it has all of the conditions we might expect for life. So the sort of things that are tying all of these topics together, like I said, are sort of phase change and ice. But also there's these dynamics of how do we know if there's potentially life in the outer solar system, and how do the dynamics that we're learning about glaciers, how is that going to affect sea level rise? So these are some of the people that I've been very fortunate to work with over the time that I've been here so far. There's a whole sequence of postdocs. Many of these people you might recognize from the Thayer and Earth Sciences community. And while I would love to talk about every one of their pieces of work today, I can't talk about all the stuff that I've done. So I'm going to focus in on one topic. I'm going to focus in on this subglacial hydrology, which the work of Aaliyah Summers and Kasia Warburton figures prominently. Okay, so I motivated some of this research with sea level rise. So what does sea level rise mean? So we can start by thinking about these are intermediate to high projections for 2050 sea level rise. And when we say intermediate and high, these are talking about the emission scenarios that we might go along. These are the typical things that we would think about. You might hear RCP or SSP, different scenarios. And so what they've done here is that they've said that this is a reasonably probable, with reasonable probability, this is the sea level rise that we will see in 2050. And what you can see from this comes from this NOAA report, and a bunch of institutions and some people in this room participated in it. And so you can see along the East Coast, we're expected to get about 0.45 meters of sea level rise, that's a huge amount of sea level rise. And what's really sobering about this report is that this is almost certainty. Right? And, there's lots of numbers that get thrown around about what the potential sea level rise we might see in the future is. And those are under different sort of collapse scenarios for glaciers, how fast glaciers go away, and lots of different scenarios. But, those collapse scenarios, they require large-scale ice sheet models, and they're run into the future, and there's a ton of uncertainty for that. Whereas this is close enough to the near future that we have really good certainty about what we're expecting to see. And it doesn't depend so strongly on those wild collapses, yet it is still quite sobering that this is tied to the year 2000, a year that many of us probably remember quite well as not being that long ago. And the sea level rise that we're going to get is still about 45 centimeters. You can see that the sea level rise is variable. It's not the same everywhere. So, New Orleans is certainly a hot spot for sea level rise. And other places are not. And that's because of the way where the sea level rise come from. So the fact that Greenland is melting is going to affect differently the East Coast versus the West Coast, and similarly with Antarctica, just because of the gravitational attraction of those ice sheets. And so this is high a high probability of that this is what we're going to see in the near future. And so we want to understand the processes that are changing so that, we can even better account for the sea level rise beyond 2050. So that's something that we're going to focus on and motivate our research for. Some of the key unknowns in glacier science involve what is the rate at which ice breaks off into the ocean. That's called calving. So if you remember that first picture on the title slide, where you had the glacier coming down and then breaking off into the ocean, we want to know how fast do the icebergs break off. That's a problem in sort of fracture mechanics, and it turns out to be a very challenging problem. We're not going to talk about that one today. But we are going to talk about the process by which ice slides over sediments, this sliding law, because that is strongly dependent on how much liquid water is at the base of the glacier, and that's why we want to understand subglacial hydrology. The last big unknown in glacier science is about the rheology and the material properties of how it fractures, and that there's been a lot of work here at this institution in the lab just sort of directly below us that addresses those questions. Again, we're not going to talk about that today because we're going to focus on the sliding law. So the image on the right here is a plot of Antarctica. So you can see it's divided. Here's the west and east Antarctica. There's a light color bar showing the velocity. You can see that there are these sort of punctuating fast regions. Those are called ice streams. But what's really evident here is what's shown in the outer part is, and that's plotted for the ocean temperature. You can see that there's a region here where there is very high ocean temperature, and it's sort of lapping up against this part of West Antarctica. And you might see West Antarctica show up in the news because this is one of these places that could potentially collapse. Why could it collapse? Well, West Antarctica sits in a bowl, sort of like you've heard that Death Valley is below sea level. Well, West Antarctica is also below sea level. And so as the warm ocean water laps up against West Antarctica, it melts it. And as it continues to melt it, the water can follow it in, right? So as it goes into deeper and deeper water, the warm water can follow. In addition, the thicker the glacier is, it actually can flow more quickly. And so there's a positive feedback where if it's on a retrograde slope, it goes into deeper sea level, it actually starts flowing into the ocean more quickly. That's called the marine ice sheet instability. So there's a lot of concern about what is going to happen with West Antarctica. And one of the interesting things is it depends really strongly on these three unknowns in glacier science. And so we're working on this one right now. Okay, so glaciers, they're hydrologically active. This was really surprising to me when I started working on glaciology. I came from a background in fluid dynamics, so I was excited about turbulence, the ocean processes, stratification, things like that. And so when I learned that those same dynamics are happening in glaciers on very disparate scales, the glacier flows like a viscous fluid on very long time scales. I'm excited about viscous fluid dynamics, so that's great. And then at the same time, there's also high Reynolds number and fast, sort of more like inviscid flow that's happening throughout the glacier because of the motion of liquid water. And then there's also porous media fluid dynamics because the water is flowing through the glacier and through the sediments. It has all of the different types of fluid dynamics. What more could you want? So I started working on glaciology, and I was very excited about how all the water was moving through it, and so I became very interested in glacier hydrology. And so how does it really affect it? And now we're going to focus in on this piece about glacier sliding that I talked about. So if we look down here at the bed of the glacier, that's what we call the bottom of the glacier, this basal interface, where we have a glacier on top and it's sitting on some sediments. And so what we can think about is just sort of a quite naive force balance. If we have the weight of the glaciers are quite thin in compared to their extent, so it's the dynamics in the vertical are primarily driven by hydrostatic pressure. So it's just basically the weight of the glacier ice. We'll call that PI, like pressure of the ice. And then pushing up, we have some water pressure. And so the sediments are in there and they're porous and they have water contained within them. And that water is going to be at some pressure. And that pressure is not necessarily going to be equal to the ice pressure because the water is able to move around, right? If it was equal to the ice pressure, then it would be effectively floating or like quicksand or something like that. And so we often think about this difference. We think about the difference between the weight of the ice and the water pressure because that is the weight that the sediments must be able to hold up, right? The skeleton of the sediments must be able to take the deficit in that force balance. And so this is a principle from soil mechanics, is Tersaghi effective pressure. And that's just written as the difference between the ice pressure and the water pressure. And it's important because it shows up in that thermomechanical interface that I talked about. And it shows up because it is the strength of the sediments and therefore is related to the shear stress that this interface is able to withstand. And so we can write that simply in this way here, and I haven't been specific about how this is, but I can say that the basal shear stress is then some function of the rate at which it's sliding and this effective pressure. And this is known as the sliding law. It's, like many fields have something that they're trying desperately for 50 years to try to understand, like the turbulent closure law or something like that. This is one of the things for glaciology. How do we wrap up all the processes that are happening at the bed into a sliding law that makes sense? Okay, so we can think about this problem sort of like a classic physics problem of a block sliding down a plane. And so if we think about you remember that the friction is then proportional to the normal force in this problem. Well, we have something similar here, except for our normal force isn't just the weight of the substance, but also has to take into account the water pressure pushing up. And so we take our effective pressure to be that normal force that is pushing down. And then we say effectively that our sliding law is then proportional to that normal force, and this F is then the friction coefficient. And so we will remember that there's, static friction versus kinetic friction. And so effectively we're saying that this friction coefficient is dependent on the rate. It's dependent on that sliding velocity. So you can imagine in sort of a naive way that's more or less how we would arrive at a sliding law for this. We would say that there's some rate dependent friction and some normal force pushing down. So then you can see that it becomes very critical for us to understand how this effective pressure, what sets the value for that effective pressure, because that sets, what we would write down as our boundary condition for our glacier, the basal traction at the bottom, how fast the ice is going to be able to slide, then depends directly on the sort of lubrication of that interface, that subglacial effective pressure. And so, based on climbing around in the Alps and other places, this idea emerged in the sort of 1960s that there are two different types of drainage systems. There's what we might think as a channelized drainage system, and here's an image over here to the left of something that's like a Roethlisberger channel. And then there's also this idea of a distributed system. A distributed system is sort of like a porous media at the interface between the ice and the sediments, where the water can move through a sort of interconnected network. And so the Roethlisberger channel has some water pressure, PW, some ice pressure, PI, and then it, generally has a flux that's going through a channel. This is the idea that sparked my interest in glaciology a bunch of years ago. Is that this is fluid dynamics, right? This is channel flow fluid dynamics. This is turbulence in a pipe, and now it has an application in glaciology, which applies to the climate. I'm hooked. Okay, so in the Roethlisberger channel, we have some flux of water that's moving through that. And if you think about Bernoulli, you can imagine Bernoulli, relating the flux and the gravitational potential and the pressure together. You could say as the flux increases, we must have the sum of all of these things must be a constant. And so therefore, if I increase this term, the pressure in the water must go down. That's sort of one way to think about this dynamic. So if the water pressure is decreasing, we find that N increases in a channelized system. And so we think of Roethlisberger channels as a strengthening mechanism. If you have a channelized system underneath your glacier, it's going to have stronger sediments, and therefore it's going to move more slowly, right? You're going to have a larger basal shear stress, and that's going to slow it down. In the distributed system, it's more like a porous media flow. So as I increase my flux, my water pressure increases, and that decreases my effective pressure. And so this is a weakening mechanism, right? So we have these sort of two ideas. There's sort of a fast mode and a slower mode for the glacier that's set by how the boundary conditions at the bed are affecting the ice velocity. So this is something that I've been working on, is trying to understand, what is the actual partitioning between these two things, the distributed system versus the channelized system. So I had just had a baby. There was nothing better to do in the middle of COVID than scrape every single paper that's ever been published in glaciology about where they measured a borehole. So that's what I did. I found 300 plus papers, and I went through data point by data point, and I cataloged all of them. And as you can see, it doesn't have a year next to it yet, so I still haven't published it, but it's coming along, I swear. And so I have, this is what that effective pressure is, and this is the number within the histogram. It's just a regular histogram. And this is the distribution here. Very interesting distribution. I can comment on that. First, we've never drilled boreholes in Africa, in Asia, in New Zealand, in Oceania. There's a very interesting distribution of where we have drilled subglacial boreholes. So I would like to go drill some other places. But coming over here where we're looking at the distribution of effective pressures, what we see is that the median value is about 1 bar. This isn't too surprising. In fact, this is what it was estimated at in the 1960s by this guy, John Nye. He expected that the basal shear stress should be about 1 bar, which it turns out to be quite close to that. 1 bar, right, is about 1 atmosphere. It kind of makes sense that that would be the dynamic because that's going to be the pressure at the end of a glacier, right? It's going to end up at atmospheric pressure. And so what we don't see from this, which is a little surprising, not too surprising since this is kind of what I expected, but in the field of glaciology, right, I said we thought that there are these 2 different modes. There's a distributed mode and a channelized mode. Therefore, it would be very nice if we saw a bimodal distribution in the effective pressure. But if you sort of squint, there kind of is a bimodal distribution, but it kind of more looks like there's a dominant peak with a long tail over here. And so this is the region over here, these larger effective pressures, where we're imagining that we're in a more like a channelized system. And this in here is where it's much closer to the 0 effective pressure. That's what we would think of as the distributed system. Also, there's a long tail on this side showing a bunch of negative effective pressures, a bunch of places where the water pressure is stuck underneath the glacier. And if you drill down to it, it actually geysers out of it. This is something that people have known for a long time. There are lots of geysering locations, and I can tell you more about that later. But the important part of this story is that it's not clear that there is a dominant mode of channelized versus distributed that comes out in our borehole data. So we need to think about that when we're constructing subglacial hydrology models. And so another way to look at this is to rather than looking at the bed, we could look at observations of the surface velocity through time. So this is satellite velocity from Greenland over here. So you can see that there are these sort of fast-flowing places. This is Helheim Glacier right here where we go to field site. That Han Glacier is right below it. And I'll show more pieces of Helheim in a little bit. Helheim's on this sort of southeast coast. Okay, so what these authors did is that this is the day in the year here, going in this direction, and the gray shows how does the runoff change. So this is basically, the center part is the melt season. This is when it gets warm enough in Greenland, so it starts melting, and then you have all this meltwater that's sitting around. That meltwater gets to the bed of the glacier, and then it begins to affect the glacier. So what's nice about this observation is that you can, they looked at all of the glaciers throughout all of the Greenland, thousands of glaciers, and they categorized them into 2 types, type 1 and type 2. And so on the top, type 1, where you have some velocity, the melt season starts, and then the velocity increases, and then as the melt season goes away, the velocity decreases again, and it goes back nearly to where it was. And so we would think that this glacier here, or these types of glaciers, these type 1 glaciers, are dominated by distributed systems, right? Because that's the faster mode. That's the one where as you put water to the bed, it can then lubricate the interface and go on. There's another slightly more complicated type, which is this type 2, where you can see that as the melt season starts, it starts to accelerate a little bit, but then the system channelizes, and it actually strengthens the bed, and then there's a strong velocity drop, and then it sort of recovers as the winter time goes again. And so we would like to see that, there's a difference in this behavior, but, this type is seemingly a little bit clearer. That it goes back to the same type value, where you can see that this one doesn't even return to the same value. So this is a compilation of a lot of glaciers that have more interesting behavior in their subglacial system. And so we'd like to understand more about that. Another way to think about this system, sort of our third type of data, it comes from Alaska. So this is the Hidden Creek Lake. Well, you can't see the label, but here's Hidden Creek Lake right here. So this is the Kennecott Glacier. This is where I went to the McCarthy Summer School here, and we walked up onto the glacier. Hidden Creek Lake so we're going, this is May, and it's going into the melt season in Alaska, and so Hidden Creek Lake is filling up. You can see it lifting the glacier up. So the glacier is back here. It's kind of an interesting perspective, but I'll zoom through it. You can see the glacier being lifted up, yeah? The crazy power of the glacier. And then you can sort of imagine what's going to happen in just a moment. Still filling. Catastrophic. So that's called a yokel up. There's a Magic the Gathering card, so it goes back to when I was a kid playing Magic the Gathering. So these happen all the time in Iceland. How many people have been to Iceland to the front of the glaciers there? Okay, just a couple of people. It's crazy there because the bridges and the road get taken out. It's a huge floodplain area because, year in, year out, there are these big yokelups, Icelandic word, that means, glacier jump. And so and that's because of all of the water that's coming out. I really like to show this. This is not clearly important to this story right now, but watch the water. So you can see when night is in this video, and watch the correlation with the water going up and down with the diurnal cycles. I think that's super cool. Okay, so that's another type of data, and so we can see this here. Tim Bartholomew, who was an undergrad here in Earth Sciences, he put out a bunch of GPS stations as part of his master's in Colorado, and he made this cool video, which is the same data, but now it's connecting the Hidden Creek Lake filling up. And so you can see the diurnal cycles in the velocity as it, day in, day out, and so the meltwater is clearly affecting the glacier speed. And then Hidden Creek Lake drains, and the velocities go haywire. And so this is definitely sort of a type 1 glacier system, right? Where you put a lot of water down at the bed, and then that accelerates the velocity of the glacier tremendously. So we sort of have looked at 3 different sort of independent lines of observational evidence for how meltwater is affecting the glacier. We looked at the catalog, which I compiled, the surface velocity observations through time, and then, this GPS dataset system showing how when a lake drains, it really affects the glacier velocity. So now we'll turn to some mathematical modeling, which is the stuff that we mainly do in my group. We take in observations and ideas from that, and we try to understand and codify them mathematically. And so this is some work that has been done led by Kasia Warburton and Aaliyah Summers. Aaliyah wrote this code as part of her PhD thesis, and she called it shock T. And so these are the equations for shock T. And so we're imagining that we're at the subglacial bed. We have some gap height here. We'll call that gap height B. That's the sort of nominal size of a little channel or a little porous media element along the bottom. And so we're thinking about a couple of different processes. We're having sort of geothermal heat coming in from the Earth. We have melting because of flow in within the gap. And then we have collapse or viscous closure of the ice. And so these different equations are trying to describe a bunch of physical processes. And so this first one is just the evolution of the gap height. So the gap height evolves in time through melting along this interface and then viscous collapse. There's a clear message. This equation is describing how water is evolving. This is taking the flow of the water here, it's evolving it in a long flow direction, and then it's adding sources to that water, a sort of mass balance for the water. So we have basal melt and then surface melt that's making its way to the bed. We take a model for the flow to be is sort of like Darcy's law, where we have a permeability that's related to the gap height. It's proportional to the gradients in the pressure. And we allow it to transition from from laminar to turbulent flow. And this is an important part of this model, is that there's a way in which here we model that it goes from, this is sort of like a Darcy-Weisbach, this is, an empirical description of channelized flow, the kind of things that I talk about in Engines 34. And then lastly, we close this system by writing an equation for the melt rate. And so this involves the geothermal heat flux, right, the heat from the earth, the frictional heat from the sliding of the glacier, and then this interesting dissipation term, right? So as I said, in glacier hydrology, you're bringing in the dynamics of slow viscous creep in contact with turbulence. And so the turbulence here, actually that heat that is generated through viscous dissipation within the turbulent cascade, that actually plays a role in producing heat in the subglacial system and keeping these channels open. It's a totally wild thought, but if you work out the analysis, there's actually enough heat through that turbulence to generate a little bit of melting on the walls. And so if you continue using that, you could actually generate over the long timescales of subglacial hydrologic system, sort of a season or a year timescale, you can generate enough heat to make a channel. And then the last term here is one that has to do with how we model the lateral heat transport from left and right for the gap height. So these are the equations for Shakti. And so this is a paper from Aliyah, and so she's evolving the Shakti equations. This is that gap height over the seasonal cycle. So it started at the beginning of the year, there was no meltwater, and then and then the meltwater started, and then there were a bunch of channels. You can see there's sort of all these channels. And then the season will go away, and the channels will start to go away as well. So we would think of this as sort of like a type 2 glacier, like one where we add a bunch of meltwater at the beginning, and then it doesn't immediately, little delay. It doesn't immediately produce channels, so we might see some acceleration, and then channels start where we might imagine that the effective pressure is becoming quite large. Here, this is showing that you get these large effective pressures in the channels, and so we might imagine that the glacier is going to slow down in this period and then sort of reaccelerate in the winter time. But when I first saw this, I wondered what sets the channel spacing in this model. So this is a very idealized model, and you can see that, oh yeah, there we go. Slight delay. You can see that you end up with about 5 channels. The domain is about 8 kilometers wide, 4 kilometers long, and it's about 1 kilometer thick. So it's not clearly related to one of the dimensions in the model. It must be set by something else. And so what we wanted to do is we wanted to figure out, what sets that channel spacing. And so what we did is we did a linear stability analysis. Okay. And to do the linear stability analysis, we started from a base case. We started from a distributed system that was a steady state. We said, okay, if we just start with a certain amount of meltwater, a certain square domain, and we figure out what is the steady state for the system that doesn't involve any channels, and that's plotted over here as on the left. We have the sort of effective pressure, the gap height, flux through the system, and the hydraulic head. And this just gives us a background steady state that's independent of the y direction. So it's just a one-dimensional profile. And then we're going to perturb it with something that varies sinusoidally in the y and has some growth rate. So we're just giving it slight kicks, sinusoidal kicks in the y. And we're asking, do those sinusoids grow or decay? The hope is that they will grow, at given wave numbers, and then that will predict the channel spacing, and that we'll get some instability. So we do find a nice instability. And so what this is showing here is the growth rate as a function of the wave number. Here is the wave number along here. And the wave number, right, is the inverse of the wavelength. And so we have, over here we have things that are close together and things over here that are far apart. And so what we have, you can see, we can look at this blue curve here. What we find is that there's a nice peak in here where we have positive growth rate for a given wave number. And so this is exactly the kind of thing that we're looking for in a linear stability analysis. We want there to be a fastest growing mode. So this fastest growing mode here tells us that, this one here is all these modes over here that are negative, those have negative growth rates. So those are stabilizing modes at the edge. And then everything in here with a positive growing growth rate, a wave number with positive growing mode. This one right here that's at the top of this curve is going to grow faster than all the ones around it. So it's going to compete, it's going to outcompete them, and we hope that tells us something about the subglacial system. And so we can run this forward. We start with a bunch of noise in our subglacial system. You can see we have very small gap heights, like 10 to the minus 4 meters, and very small variation around it. And then we have the growth of small perturbations, and then the channels take off. And so let's see, we'll do this slowly. So it starts with a bit of noise, and then you can see that the channels start over here on the left. You can see the initiation of the channels, and then the channels compete against one another, and then there's a dominant, there's channels that grow along here. So the nice part about what we described is that we determined that there is an instability that's kicking off, that's making these channels. But what you can see from this is that it's not predicting the final channel spacing, right? Here we are getting about 3 channels, whereas in this last figure, what we saw is that the channel spacing is closer to the sort of like meter scale. Here, this is, if you take 1 over that, and there's a factor of 2 pi, you're on the sort of something like the meter scale. And here, this is, we're on the kilometer scale, and we're getting 3 channels. And so what we determined was that that our instability works great, but it just tells us about the initiation of those subglacial channels rather than the final outcome of what they would be. So it doesn't tell us what the channel spacing is. We're working really hard on that. But it's a challenging problem because it's clear now that those are not a linear mechanism, right? We did a linear stability analysis. We hoped that our linear stability analysis would predict the spacing. But what we found is actually it's a nonlinear process that's doing that. So now we're doing a bunch of nonlinear pattern formation. So stay tuned for that. But what we did find is that our analysis does a really good job of telling us whether a system should channelize or not channelize. Which, if we go back to our motivation about distributed versus channelized systems and type 1 and type 2 glaciers, that turns out to be kind of important. So here what we have is on the left is showing as a function of how much meltwater is going in and the ice thickness, we can predict whether there's going to be a channel or not. And so there's channels up here in the red. This is the positive growth rates. And there's no channels in the blue. And, the X's and the O's and the line and the dots, so those are just a bunch of different ways of computing the same thing. But effectively what we can see is that this dashed line is the analytical solution that tells us where that fastest growing mode is. And that does a really good job telling us when things transition from blue to red. Or equivalently on this side, we can see that this is the size of these elements, the spacing, and we can see that the white dashed line does a good job of saying when it goes from 0 to something positive. So we can apply this to glaciers in Greenland. This is some ongoing work that we're doing. And here is that same plot that I just showed on the last figure, but now I've changed this for a bunch of different parameters, and I've included the transition from turbulence to laminar. But effectively, you can imagine that on this side of this curve, we have no channel, and on this side of the curve, we have a channel. So we can ask for different glaciers, for their different geometries and how much water we would expect, whether there would be a channel or not. And so we ran this is a case for Shakti. We ran Shakti for for a pair of glaciers that are right next to each other. So this is IS and then Russell Glacier. This top IS, you can see that there's this sort of yellow channel system here. And at Russell Glacier, there's no channel. And so when we run our analysis for this channelization criteria, this stability criteria, we see that there should be a channel at IS and there should not be a channel at RG. And so the ongoing work that we're doing right now is that we're going around for thousands of glaciers in Greenland. We're extracting their water flux and the ice thickness, and then we're just saying, based on these, should there be a channel or not be a channel? And then we're going to use that to correlate with the behavior around type 1 and type 2 glaciers to see if this is a simple way to say something about the subglacial hydrology. Okay, so the next vignette will be going to Helheim Glacier. which is in the southeast, so we're just going right across the ice sheet. This is Helheim Glacier here. This is the terminus. This is the ocean. And this is a photo that I took from a helicopter, and I'll show you that now. Here's the terminus again. It's a little jumpy, but you can see all these meltwater on the surface, sort of ponding. That's making its way into the glacier. And so, I took this in the summer when it's nice to be there. And you can see there's a big meltwater lake that shows up on the surface right there. Yeah, you can see it turn a little greenish blue. So this is one of the, and then this is this Nunatak big rock in the center of Helheim. So this is another view of Helheim. This is our computational domain for Shakti. Helheim's a really big glacier, very important. It's the largest contributor to sea level rise in the northern hemisphere. And it's really stubby. It's not very long. It transitions. This is the ice, center of the Greenland ice sheet, and then this is the ocean down here. So, over just about 25 kilometers, it transitions from the interior of the ice sheet to the ocean. And so this is a very strongly terminus-driven glacier. It means that the ocean has a strong effect on how fast the glacier is moving. And so this is some smooth data for how fast the glacier is moving at the front. It's ripping along at about 6.5 kilometers per year. And we have strong melting at Helheim. There's a lot of surface meltwater there. And so what we wanted to know is, Helheim doesn't fit perfectly into this type 1, type 2 system because of this strong terminus effect. And we wanted to know, how does that terminus effect propagate upstream, and how does that affect the hydrology? And so if we look at this point C up here, which is, a decent way away from the terminus is here at point A, we can see that the terminus influence has been lost at point C, and that it no longer looks like a sinusoid here. And so what we have here is that this point up here is dominated by the hydrology. And so in order to quantify this a little bit more, we made maps of how the hydrology is changing throughout the year. So you can think about this as sort of like an expanded version of this type 1, type 2 thing, but now we've added into the terminus effects. So before the melt season, the glacier velocity, here's the Helheim glacier velocity, that's dominated by the terminus. And then at the end, again, you can see that after the melt season, the terminus effects are dominating the glacier velocity. But in the middle, what we see is that there's a very strong hydrology pulse that's affecting this upstream region. So you can sort of see that the bottom tongue of Helheim, this part right here, is basically dominated by the terminus all of the time. But the important parts that are sort of activating this larger region that's sort of supplying the ice that goes into the tongue, that's activated by hydrology. So there's kind of a dance between the terminus and the hydrology that's happening here. And so why is that important? Well, we know that as climate is changing and there's more meltwater on the surface, we potentially are going to get larger activated zones that could be feeding into the front of this glacier. And so one of the things that we're trying to do now is we're trying to run these into the future. We're trying to say, okay, how will this change as we get more meltwater, and how the terminus, if the terminus retreats, we could be activating more of these regions. And so that's something that we're working on actively. Okay, and as the last little closing vignette, there's been a bunch of high-profile articles in splashy places about, it feels like we can't do anything about climate change, so what if we tried to do something about climate change? Is there anything we could do? And I think that this gives people a lot of hope, and a lot of people get very scared because they feel like it might be giving them false hope. I can tell you that when the New York Times Magazine puts a price tag on the amount of money it might take to fix a glacier, that makes me very scared. And so what's some of the ideas? Well, we can tie this idea directly into the research that we've been talking about today. The question is it possible to pump water out of the glacier or put water in? Is it possible to do something about the subglacial hydrologic system that then has a direct effect on the velocity, right? As you could imagine, if this was a type 1 glacier and we drilled down to the bed and we extracted the lubricating effect, we could shut down that velocity acceleration. That seems really promising. And so what we've been trying to do is determine whether that is an actual possibility. We want to know whether this is something that we should even be thinking about before we can make decisions about, whether we shouldn't be investing whatever $500 million into it. So the nice part is, as you have already seen, we have the kit set up to do this, right? We've been dumping lots of water in our numerical model into the Helheim Glacier and watching it accelerate and change. So we asked the question, what happens if we do the reverse? We take the points that we've been inputting water into the glacier, and then we run it backwards. We just flip the positive sign for the meltwater into a minus sign. And so here we took 1 point. So you can see here's the Helheim outline here. This is the background effective pressure, and it's at this point in the confluence. This is the sort of like terminus region of Helheim. We already know from the last vignette that doing this at the terminus wouldn't really help because it's mainly driven by the terminus effect. So we would want to do this in some upstream region. So we chose this confluence point. And so this is a zoom in of that region, and we can see if you sort of squint your eyes and ignore the numerical resolution, it kind of looks a little bit axisymmetric. So we said, okay, maybe we should analyze this in an axisymmetric geometry, which turned out to be kind of a fun problem. We wrote out axisymmetric shock T. We then did a bunch of numerical and analytical analysis, and we were able to determine what does the effective pressure look like as a function of the radial distance away from the borehole. So this is asking these two key questions. Sort of what is the radius of influence, and what is the effective pressure at the location of the borehole. We want to know the radius of influence because we want to know how many of these would we need to use in order to potentially slow down Helheim. And then we want to know what the effective pressure is because we want to know, how big of an effect on sliding is this going to have. So, as I said, I had a bunch of fun. We did a bunch of analysis. And there's sort of two answers to this question of what's the radius of influence. As you can see, this is for a 10-kilometer geometry, and the borehole effective pressure is elevated throughout all 10 kilometers of it. This is sort of decently to be expected, right? We're solving Laplace's equation in 2 dimensions, which if you've done that, you know that there's a logarithm that shows up. That logarithm means that even if you go far away, it's actually never decaying away. It's not like solving Laplace's equation in 3 dimensions for a sphere or something like that. So that's basically why we end up with this log term here. So that means that the radius of influence of the extraction, well, it's like as far as you go out until the rate at which you're pulling the things out is, now minuscule compared to the background effective subglacial hydrology. But more realistically, the radius of influence happens when you transition from turbulence to laminar, because that's when the dominant effects happen. The laminar is not going to have as large of effect. And so you can sort of see that as a transition, as this sort of like drop off over here. And so the transition from turbulence, you're near the borehole where you're extracting, you're expecting the water flow to be quite turbulent, sort of like, as you could imagine in the subglacial system. And then as you get, about 100 meters, maybe a kilometer out, you're going to no longer have any turbulence, and you're going to go back to something that looks much more laminar. So I would say that, that transition to turbulence, should shock T be a good representation of this subglacial hydrologic system, that would be what I would say would be the radius of influence. And the next question is sort of what is the effective pressure at the location of extraction? Well, if I run my analytical model, we find that there's, a transition here to something that looks like about a constant value. And then I do this for a bunch of different extraction fluxes. Then I can plot, what is the effective pressure? How does that vary as the extraction flux? I did it for a bunch of unphysical values. Thinking about 1 cubic meter per second of water extraction, that takes a pump the size of like a Toyota Tacoma or something like that. So you can imagine that, having 100 Toyota Tacomas, that's a big pump, and that doesn't really exist. But we could imagine putting, a couple of those big pumps in there. The question is about the water availability and the ability to actually extract water at that rate. Okay, so then so basically what we learned from this is that, we might not be able to extract a lot of water at a single point, and that the radius of influence might not be very large. So it might be better to imagine doing that at a bunch of different points and having sort of a pumping type schedule. where we're imagining extracting, say, something like 2 cubic meters per second for 30 days at a bunch of different points. And when we do this and we run this in the model, we find that we get a slowdown on the order of a couple hundred meters per year, which is not negligible. It's less than 10% of the glacier velocity, right? Remember, it's flowing at about 6.5 kilometers per year. But the regions that is most effective are outside of that trunk region, which is dominated by the terminus. So it's possible that we could starve the trunk of some downstream ice, and over a long period of time, that could actually slow it down. And there's glaciological evidence for that happening in places in Antarctica and other places in Greenland. So it's not totally a crazy idea, but there is so much research that we would need to do before we would ever want to say anything that came anything close to advocating for this idea. So with that, I'll just wrap up, say that we talked a bunch about subglacial hydrology and how it affects the ice velocity. We talked about the zones of influence and the different types of glaciers and how we might set up channelized systems versus distributed systems. And we also talked about some zany ideas about how this might be a way that we could consider intervening in the glacier system. So I'll take your questions.